In this video, what we're going to look at is we're going to look at the topic of trig graph transformation. So that's transforming your three basic trig graphs using a variety of properties. Now, we've done graph transformations before where it's just a generic function. What happens to it when we move it? What we're going to look at here is specifically what happens to the three trig graphs that we know. Now, we remember the three basic trig graphs look like this. So you've got y equals sine x, y equals cos x, and y equals tan x. And they've all got their key properties. So for example, for sine x, you've got the values located at 0, 90, 180, 270 and 360 degrees. At 90, sine is 1, 270 sine is negative 1, and at the other three points it's 0. Cos is just sine but shifted 90 degrees to the left a bit. So you've still got a maximum of 1 and a minimum of negative 1, and the five key points, 0, 90, 180, 270 and 360 again. They're just slightly different. So in this case, 90 is at 0 where it cuts the x-axis. 270 is at 0 where it cuts the x-axis again. Tan x is this one here now. Tan x is the awkward one, remember, because it has the discontinuities at 90 and 270 degrees. It goes off to infinity as it approaches 90 from below, and it's at negative infinity as it approaches 90 from above. Remember, this comes from the fact that we know tan x equals sine x over cos x, so we can use that relationship for it. And at 90 and 270, cos x, as you can see from the graph, is 0. So we're essentially dividing by 0 at that point, hence these discontinuities. Now, we can transform all three of these graphs using the same set of rules and the same set of properties. And that's when they look like this up the top here. So you can transform them of the same form. Y equals a sine of bx plus c plus d. Y equals a cos of bracket bx plus c plus d, or y equals tan of bx plus c plus d. Now we'll see in a second why we don't have an a with the tan one, because that really doesn't do much to the graph at all. Now, similarly to the graph transformations we've already done, it's the same sort of idea for each of these. So now the a is in front. Imagine the a is like the graph transformation when we covered y equals a of f of x. So when it was looking like that changed the magnitude of the size of the function, and it has the same effect here. So if the size of a is bigger than 1, it stretches it in the y direction. If the magnitude of a is less than 1 but bigger than 0, it squashes it. Okay, so it stretches our graph in the y direction, or it squashes our graph in the y direction, depending on the value of these. The b, which is in there, again, that's very similar to when we did the graph transformation of y equals f of bracket ax. Now this took the graph and stretched it or squashed it in the x direction, but it was again counterintuitive, because in this case, if the size of a was bigger than 1, it actually squashed it. So it actually squashed it in the x direction, whereas if the magnitude of a was between 1 and 0, it stretched it in the x direction. Now, this also leads us to a key property with trig graphs. Trig graphs have something called a period. Now, this is how often or how long it takes them to repeat themselves. So if you think back to the basic shape of a sine or a cos graph, the basic sine graph and cos graph repeats itself every 360 degrees. If we then look at ax, so let's imagine we had 2x, 3x, a half x, that's going to change how long it takes to repeat it. So for a sine or a cos, what that does is it does 360 divided by a, tells you how long it takes to repeat itself. So that tells you the period of the graph. But like I say, that's for sine or cos. Tan is slightly different because, again, think of the shape of the tan graph. It repeats itself every 180 degrees. So for the tan graph, it's 180 divided by a. Tells you the period of the tan graph. C, which is in here, affects where we are in the x. So this is similar to when we did y equals f of bracket x plus a. That shifted the whole graph to the left or the right. In this case, if a was bigger than 0, so we had a positive value, you would think you'd shift up, but remember x tends to go the opposite direction. So if a was bigger than 1, it moves left by a. So it moves left by however much the value of a is. And if a was a negative value, so if it was less, it moves to the right by the value of a. We've then got the last one here, the plus d, and again treat that the same as when we did y equals f of x and then the plus d outside the bracket. This affected the y direction because we already have our function and shifted it up or down. So if d was bigger than 0, what it did was it moved up by d. And if d was less than 0, it shifted down. So it moved the whole graph down by d. These were your 4 graph transformations that we're going to focus on when we're doing the trig transformations. Now, when we're looking at them as well, there's a certain order we should approach them. BODMAS, back in basic calculations, BODMAS tells us the order to do things is brackets, indices, division, multiplication, addition, subtraction. Think of transformations as being the same sort of order. When we're doing transformations, the first thing you look at is the bracket section here. And the first transformation you do within that is the multiplication one. So the first transformation you should always look at is the bx. The second one you should then look at is the plus c. So do the transformations here first, see how the graph shifts with those. Then approach the rest of it the same way. So you do your multiplication first. So the third transformation we'd look at is this one. And then the final transformation we do is shift it up or down by plus d. When you're transforming the graphs, always use these 4 steps in this order. It'll just make it a heck of a lot easier for you. Let me show you what I mean. So let's imagine I want to plot the graph of the function y equals 2 sine x plus 1. Now think of the order that we were to approach it. The first one is look at the bracket section here, but this is just sine x, so there's nothing being affected in there, so we can ignore that to begin with. First transformation we'd then look at would be the 2. So the first one we want to think about is how it would look if we had y equals 2 sine x. Well, we know that that is going to have an effect on the magnitude of the graph, so this how tall it is and how short it is. 2 here means that we stretch it. So we take the y equals sine x graph and we stretch it in the y direction. And it stretches up to the value of a, so in this case it stretches up to 2 and down to minus 2. So what we've done is we've taken the graph and stretched it in the y direction just as this transformation would do. Has it done anything to the x's? No. So it would still cut at 0 to begin with. There would be our 180 degree x-intercept, and there would be our 360 degree x-intercept. So this would be our graph if we just had y equals 2 sine x. Now we've got one more transformation to do. We've got the plus 1. What we know that's going to do to the whole graph is shift everything up by 1 in the y direction. So it's going to shift our minimum value here at negative 2 up 1 to negative 1. Our maximum value is going to go from 2 up to 3. And our y-intercept is going to go from 0 up to 1. Shape of the graph is still going to stay the exact same. It's still going to look like that. It's just going to have moved. Now you could imagine this dotted line here, which we can add in, is what would have happened to the x-axis. So the whole thing is shifted up. Final value here is still going to be at 360 degrees. And that little bit there is still where 180 degrees would have been in the x. It's not moved. What has moved is our 0 has gone there to 1. Our top value has gone up 1 from 2 to 3. And our lowest value has gone up from negative 2 to negative 1. So what we've got here is our graph. And at this point, do not forget to label it and tell them what you've plotted. So in this case, y equals 2 sine x plus 1. That's me plotted it, that's me drawn it, and I've shifted the entire graph as required. Now, this isn't the only transformation obviously we can do, but we've done it in the order we said. Let's imagine we throw in a couple of more. So let's imagine we now want to plot the curve y equals 2 cos of 2x plus 30. So let's imagine we want to plot this. So again, we'd approach it the same way. Look at the bracket and start with the transformations in there. We've got some, so we have to do them first. And the first one we'd look at is this bad boy here, the 2x. So we'd want to plot y equals cos 2x. Now think back to when we talked about what that does. 2x here would squash the graph and make it repeat twice in 360 degrees. So it would take our cos x, and instead of just having one repetition in the 0 to 360, we'd have two. So it would look something like this. We know our first repetition would occur at 180 degrees, and our second would occur at 360. Maximum and minimum values, nothing would change for that. They would still be the same. So this would be our y equals cos 2x graph. Our second transformation would be the part in here, the plus 30. So what that's going to do is that's going to shift the entire graph by 30 degrees in the x direction, but we're adding 30, so it's going to shift it left by 30 degrees. So every single value is going to shift along left. So what that means is our graph, this point here will shift here 30, but we're not interested in that because it's below 0 at the moment. So it would start somewhere around about here, and it would then curve as normal. We'd then have our second repetition of the cos graph, but it would then come down a little bit more to give us this extra little section here. So think of it being there. That's them at the exact same height. And that would occur at 360 degrees. Now, what's going to happen to each of these values here is they're going to shift left by 30 degrees. So this value here was at 90. This value here was at 270. So each of them is going to shift left by 30 degrees. So when they shift left by 30 degrees, the minimum value here, which was at 90, is going to go across and is going to go at 60 degrees. Our maximum, which is at 180, is going to go down 30 and go to 150 degrees. 270 is going to go down to 240. And our one that was at 360, our maximum there, is going to go down to 330 degrees. Nothing's going to happen to the maximum. So our maximum height is still going to be the same. That's had no effect on it, so it's still going to be at 1 and negative 1. And that would give us the graph y equals cos of 2x plus 30. So that's two of the transformations done. We've got the final one now, which is this here. Now this will affect the magnitude of the graph. It is going to affect how tall it is because that is going to stretch it in the y direction. It's going to do nothing in terms of the x direction that we've not done already. So all of this is still going to have happened. So our graph is still going to look something like this. Curve of the cosine going down there, back up, and occurring just off the peak value at 360 degrees. Our 360 would still be there. All of the x values for our maximum and minimum would still be the same. So that would still be 330. U would still occur at 240. This maximum here would still occur at 150. And the minimum here would still occur at 60 degrees. The big change now is the height of our graph. So the maximum and minimum, 2 cos x. So what that does is stretches it out and makes the maximum and minimum go from 2 to negative 2. Final thing, always do this at the end. Make sure you label it. Tell them what you've plotted. So in this case, I've plotted 2 cos of 2x plus 30. When we're transforming the trig graphs and moving them around, follow these steps. If you do this and do it in this order, you'll not get yourself confused and you'll nail it every single time, as long as you remember how each of the transformations works.